Our last speaker before the break is Eric Dull. Eric is a technical director at Cray. He spoke briefly this morning and presumably will give us more information. He guides large data science and cyber applications for a variety of U.S. government and commercial customers. He's a recognized expert with respect to demonstrating mission successes using applied graph theory, data mining, anomaly detection, and data quality algorithms. So,
cool. Thank you very much.
Eric.
I'd make a joke about me not knowing Windows, but you heard that already. Okay, so this is one of the most fun things I get to do every year, which is play network analyst on a really, really big network. There's a small proviso going into this briefing. I had to submit the abstracts before I did some of the work. So we're going to talk about some of the really fun things we did, then we're going to say we wish we had more to say here, but we were too busy hunting down these bad guys. So what is SCinet? Has anybody heard of SCinet? Okay, cool. SCinet is like one of the most fun things on the face of the earth. There's about 300 people over the course of a year that all get together to make this network happen. It stands up for about 2 weeks every year. It's public IP space on loan from one of the national labs. So every year we organize, get together, plan, stand it up, run around like headless chickens for about a week or so, tear the whole thing back down, continue to drink copiously, and think about the next year. We've got a /17. This is non-filtered space. This is going to become very important in about 3 slides. So we talk about dumb things that people who get booths do. It supports the technical conference, but also the exhibition hall. The way that it works is that each of the universities, vendors, et cetera, that want a connection to their booth pay to have a connection to their booth. In some cases, it's 100 gigabit a second. In some cases, it's 1 gigabit a second. Last year, we ran 1.2 terabits a second onto the show floor. That's really cool. We had about 11,000 devices. I think that number is actually low because we had 14,000 attendees this year. And we had about 300 gigabits a second under Bro observation. 200 gigabits of that were using Reservoir Labs gear. And then about 96 gigabits a second were using commodity servers. This is the really big wiring diagram. Exactly. The part that we care about is right here. This is the network security portion of this diagram. The Reservoir Labs gear, you can see that up there at the top, Dominate 1, Dominate 2, and those are our 200 gigabit taps. The Sec Bro gear is on our left-hand side. We also had Big Bro where we tried to run the Elk stack. We just didn't have enough software, or enough oomph for it. We're planning to do better next year. Cray had a graph visualization box that we used for a bunch of our data prep. And then we used some Metaflows and the Supermassive provided by Dell. How much data did we get? The answer is a whole lot. You heard me talk about triples a little bit this morning. For everybody who thinks in triples, read on the right-hand side. For everybody who thinks in like actual data, read on the left-hand side. Short version is we got on order of about 1.5 billion flow flow and other associated Bro output over the course of about 5 days. That turned into about 18 billion triples, RDF triples. And as you saw this morning, we've been talking about the OCOG format. This was the first time we used it in Anger, and it turned out pretty well. I made them shorten a lot of human writable things because I got tired of typing it over and over again. This is the amount of traffic we got. Dr. Collins here, this is the point he'd point out that my scale is Y, my log scale is Y. That's because we found a couple, shall we say, significant events right quick. The first SYN flood was outbound from the conference floor. So a booth, who shall remain nameless, it was went live about 8:45, 9 o'clock one night, and spewed a SYN flood out into the world for about 12 hours. So in fairness, we discovered this at 3:45 in the morning when one of our security colleagues woke up and said, I have a 2-week-old, and by the way, we're SYN flooding Jabukistan, right? I confirmed it at 4:30 because I have trouble sleeping. We couldn't turn it off until somebody came to the booth and they said, oh, that's kind of bad. And we said, yeah, it is kind of bad. And they said, oh, that's just a VM. We don't need that anyway. And so they turned it off. Yeah. The only other thing to pay attention to on the chart is you can see that we have a whole bunch more number of flow off the commodity links than the 100 gigabit links. This is because we tend to move a lot more data over the 100 gig links. And that's not the way that we are advertising the routes out to the rest of the world. So flow does not directly equate to bandwidth used. What we were trying to do, besides look for guys just running random SYN floods using volumetrics, was really trying to identify that outbound scanning or attacking for reputational IP security. We're going to reuse this IP space. Let's not put it away dirty, because it's going to be a bunch of blacklists the next time we want to go use it. Cray, as part of this, helped identify groups of infected systems, performed that next hop or follow the flow that I talked about this morning, and we worked on using streaming analytics to automatically identify new DNS and DHCP servers. I'm going to walk through how you too can do some of this stuff by showing some example code after I describe each of the operations. We did 3 types of things. We should never apologize for being able to search our data, because it's really, really hard to search some of these volumes. And so most of the stuff we did was just searched for traffic that looked like this. 1, 2, 3 hop, used intrusion detection system alerts to filter and seed our subgraphs. We did Jacquard scoring, which Bob talked about this morning. And we also used betweenness centrality a little bit as an example of another algorithm that could be applied in this context. So here is an actual graph, unlike the one I showed this morning. The way the nodes on this work is the lower left-hand corner. That would be like Tijuana, if this was the United States. That is a node showing the IP addresses engaging in SSH password guessing according to Bro. The middle nodes, the laptops, are external IP addresses, and the houses are inside the SCinet space. The way we built this graph was we started with password guessing. We say we're looking for hosts that are involved in SSH that have at least 10,000 response bytes in the paired session flow. This is useful. This is helpful. This is not grep. That's a big selling point. The node way up in the corner up there, 251, 254, that's our backup DNS server. We discovered this the last day, and we ran around like headless chickens for a while, and then we decided to shut the network off. But the reason that we visualized this was because, you know how I mentioned this was unfiltered IP space, free and open? Some people didn't read the service agreement very well when they signed up for their booth. And so a lot of people brought weak SSH passwords on a bunch of their boxes. And there's a Linux worm that's running around forcing SSH passwords. At least there was over November when we did this. So this meant that we basically spent 5 days going to a booth and saying, hi, somewhere in here at this IP address, there's a weak SSH password. And they say, oh, how'd you know that? You said, well, because you're trying to infect Jabukistan again, right? And we did this 4 times a day for 5 days. As you can imagine, the analytic workload of doing that repeatedly is non-zero. None of us were dumb. It's just, we had a bunch of Sandia Labs guys. I was there, some other guys were there. This just requires time to find, vet, approve, go find the guy, get ready to throw him off, et cetera. How do we build that? So I mentioned Sparkle this morning. This is my make it so everybody else can do this sort of graph visualization stuff. This is Sparkle. Reading from the bottom to the top, we can nest our select statements. Select statements are very much like select in SQL, where they give me a tabular view or a list of things. So here I'm selecting AP addresses and internal addresses, where the AP is the external thing that's doing the password guessing. You can see where it says password guessing on that first line. And then I said I'm looking for port 22 in my destination port. Then take those and match them against the next set of stuff to the select statement. And then the construct builds the graph for me. So I've got a 2-hop here because I've got the 2 select statements. I can say I want something other than port 22 or TCP if I wanted to modify this or proceduralize it to make it so that people can visualize kind of any connection graph using the same code. So Jacquard, I like Bob's Jacquard picture better, but this is mine. Jacquard is the intersection of the neighborhood size of V1 and V2 divided by the union. I know his is better. I just said that. You can see the nested select statements here. The inner select builds me the numerator, and the outer select builds me the denominator, and then I could just divide one by the other. So why would I bother to go do this? I'd go do this. You know, I mentioned the guy who went active at 8:45 at night. We actually got an IDS hit off of him where we saw him doing this ELF binary download on port 9162. And so I said, here's port 9162. Let's find everybody else who's communicating on 9162, and let's find the other ports that they're communicating on, because I'm looking for C2 channels. Because I want to cut this guy off at the knees as fast as possible, because I don't want to chase him around all day. And so we applied Jacquard scoring and found 7668. It turns out that that indeed was a good port for us to use. And here's a visualization with 7668 at the top and 9162 at the bottom. So between this centrality, I mentioned Jeff Janey's and Mike Collins' work from 2011 here. It's good, you know, I like between a centrality. It finds you the most central node in a network, or the most central set of nodes, kind of the thing that's tying together, or the place the information flow is going through. In my toy example over here, C is the most central node. In the Sparkle code way over on the left, the most important part about this is that invoke YD graph algorithm between a centrality. Cray has taken some open source code, MTGL, for those of you who like to play graph, that's written in C++ to run on some of our hardware, embedded it in to our Eureka system that does Sparkle, and make it so you can call C++ algorithms, graph algorithms, over subgraphs you build in Sparkle. So this is how we make this generally accessible without making everybody learn how to program C++ on a really finicky hardware architecture. If you like talking about that, come find me in the break, and we can talk clock cycles and no L1 cache and terabytes of RAM and lots of really cool things. I don't like that, so I just like using somebody else's implementation so I don't screw it up again. But here is the connection network around the guys who are doing SSH Forcer. You can see where it says SSH Forcer kind of blurry there. He's the only guy who doesn't have a picture. Then we see external nodes who are then logging into things, who are logging into other things. Between us centrality shows us that if we were to try to tear this network down, or if we were concerned that there was a live component, an interactive component here to people hacking across these connections, that would be the node to start with, because that is going to give us the most bang for our buck in terms of remediative action. We can also use between us centrality when we're doing something something like looking at BGP routes to determine vulnerabilities in your network configurations. Basically, these 2 or 3 servers, if they were to come offline, would really hurt your network. It would really hurt your availability. Most of us can know this because we look for the uplinks and say, if that goes down, I can't go read XKCD. Richard Clark basically performed this practical analysis as one of his early books, one of his fictional books. So, and here's visualization of what these results look like. I've obfuscated the IP addresses due to the ongoing sensitivities. We're pretty happy with this work, and I know I'm giving you the 50-mile-an-hour view at 1,000 feet. But we were able to use graph techniques and a graph engine to identify outbound scanning behaviors, looking at this dispersive behavior, as we call it, where you see a large outbound degree from a given host. We were able to identify these candidate C2 hosts and nodes using Jacquard scoring. Some of the port triage stuff that I didn't show you was pretty nice, where we were able to just look at a report and identify where some of the downloads were coming through. And then we used Spark streaming to identify DHCP servers that were online, because we were really concerned during these wireless troubles that we actually had a rogue DHCP server on the network. The troubles happened when the primary DHCP server kind of failed silently about a week into prep at the conference. That wouldn't be so bad, except the backup server was hosted on a VM that had a really a resource-intensive database server also on the same bare metal. And so basically, we resource-starved our only DHCP server serving the wireless network, and we kicked everybody off the wireless network for about an hour, which at a conference, when you didn't really want to listen to what they were saying, is not really good network service behavior. So where are we going now? We mentioned we've got this NetFlow way to look at data in RDF. And we've got a few other scripts that we wrote in the last couple of years. We don't have one for DNS. That's a big problem. Mostly for our uses at SCinet, it doesn't really matter. But to reuse this code in a more generalized context or for larger enterprises, that's kind of a big deal. Somebody asked me during the break this morning, what is OCOG probably going to do next? That's where we're leaning. Improved Python parsing. So the box that we use for this has a number of x86 cores on it. We just need a better way to generate this RDF faster. We were on about a 60-minute cycle because that's as quickly as Bro could turn over and give it to us on the commodity hardware. And on the special purpose hardware, we were on about a 15-minute cycle. That's great, and we solved a lot of our data movement bandwidth issues through some legwork we did over the last year. But I'd like to get that down to 5 minutes if I can to generate data and have it online, because that makes this a much more usable and tractable approach. And kind of the last big thing is that those visuals I showed you were based off of a thin client viewer that we wrote inside Escape Web. There are other better approaches, and there's something I'd like to make scriptable, so I can just generate PNGs, and that makes it easier to put into reports and automatically put it onto dashboards and handy things that people care about. So if you believe that I'm interesting enough to at least go run my Sparkle code and see if I left any typos in it to catch you, there's a few places you can start this. I'm number 2 for referencing Dr. Collins' book. I think we should make this a drinking game. But he's got a whole section on graph analytics and graph analysis. Mark Newman has a great publication section around social network analysis algorithms, particularly applied to social graphs as opposed to computer network graphs. But they have some really nice properties, and I think we could easily apply them to trying to take those CDNs that are kind of a pain in the butt and clustering them based on connective behaviors. And Linked by Bear Bossi is a book with no math in it, but actually explains graphs pretty well. If you wanted to go do this, I mentioned MTGL, there's a link for it. Apache Jenna is an open source Java-based RDF Sparkle engine. Cytoscape and Gephi are thick client viewers that you can go download, get data into, futz around with, make nice pictures. And the Ames Labs guys showed some pictures out of Gephi this morning. So I think I'm good on things I want to say. Do you have any questions? Cool. We all get to go have a cup of coffee. Thank you very much.